Assalamualaikum warahmatullahi wabarakatuh and good day to everyone. Today we from Group 6 want to presenting about second order linear differential equation and Laplace transform. First, we want to introduce ourselves. My name is Raja Haikal Najmi bin Raja Hussin. My matrix number is CN250104.
Assalamualaikum warahmatullahi wabarakatuh. My name is AMMAR SYARIFUDDIN bin Muhammad ZARAWI. My matrix number is CN250042.
My name is HAQIM bin ZULKIFLI and my matrix number is CN250100.
Assalamualaikum warahmatullahi wabarakatuh. My name is KAMAL bin Muhammad SHUKRI. My matric number is CN250089.
Hi, Assalamualaikum. My name is ABDUL bin Abdul TALIB. Matrix number CN250302.
Okay, for the next slide, I will present about the introduction to differential equation. First, differential equation is an equation that involves a function and one or more of its derivative. It is used to describe how a quantity changes with respect to another variable, usually time. The general form of a differential equation can be written as dy per dx equal f of x y, where dy per dx represent the rate of change of a function. Differential equations are important because many engineering problems involve changing quantities. Because, for example, engineering use differential equation to study mechanical fabrication, electrical circuit, population growth, heat transfer, and control system. Through differential equation, engineer can analyze or predict how a system behave under different conditions. For the next slide, we are going to look into second order differential equation. To put it simply, what defines a second order differential equation is that it contains a second derivative, denoted here as y double prime. If you look at the slide, this is the general form that we use to represent it. A y double prime plus b y prime plus c y equal f of x. To break this down, a, b, and c are constant. Y double prime is the second derivative that identify the order of the equation, and f of x is what we call the forcing function. Depending on the nature of this forcing function, we can classify this equation into the main categories. Homogeneous when f of x equals 0, and no homogeneous when f of x is not equal to 0. For the next slide, we move to important in engineering. Why is this important? Because engineer use this equation to predict system behavior over time. Key applications include spring mass system, electrical RCS circuit, structure vibration, robotic control system, and the last, aircraft dynamic. In short, it is an essential tool for designing and modeling real-world engineering system. For the next slide, I pass to AMMAR Sharifuddin.
Okay, thank you Haikal. For the next slide, I will present about homogeneous and non-homogeneous differential equation. Okay, uh, how to know which homogeneous or non-homogeneous in differential equation? As you can see at the slide, if fx is equal to 0 in equation 1 and equation 2, then the equation is known as homogeneous equation. And then if fx is not equal to 0, the equation is known as non-homogeneous equation. Okay, for the next slide is introduction to homogeneous equation. The second order homogeneous linear ODE with constant coefficient refers to an ODE of the form a d prime y over dx prime plus b dy over dx plus c y equal to 0, where y is the unknown function, dy over dx and d prime y over dx prime the first and second derivative of y, a, b and c are constant. The word homogeneous means the right hand side is 0 because there is no external input of forcing term. Okay, for the next slide is method of solving homogeneous equation. Okay, this slide um, explain the method of solving homogeneous differential equation using the characteristic equation method. Okay, first step is start with the second order homogeneous differential equation. A d prime y over dx prime plus b dy over dx plus cy equal to 0. To form the characteristic equation, we replace the derivative with power of m, giving am prime plus bm plus c equal to 0. Okay, for the second step is solve the characteristic equation to find its roots. This root determine the form of the general solution, depending on whether the roots are distinct real root, equal real root, or complex root. We use the corresponding solution formula. For the next step is determine the general solution. Three cases arise according to the type of roots. Case 1 is distinct real roots. Case 2 equal real roots. Case 3 complex roots. Okay, the next step is if given the initial or boundary condition, substitute to the solution to obtain the value of A and B. Okay, for the next slide, this slide shows the three possible type of roots for a second order differential equation and their corresponding general solution. First, for distinct real roots, when the roots are m1 and m2 they are different, the general solution is the sum of two exponential function y equal to a exponent m1 x plus b exponent m2 x. For the second is for equal real roots. When both roots are the same, m1 equal to m2 and m. The general solution becomes y a plus b x exponent mx. The extra bx term is added to ensure two linearly independent solution. Okay, for the third is for complete roots. When the roots are m1 equal to alpha plus beta I and m2 equal to alpha minus beta I. The general solution is y equal to exponent a x. A cos beta x plus b sin bx. This solution combines exponential and trigonometric function and often represent oscillatory behavior. In summary, the form of the general solution depend on the nature of the roots, distinct real roots, equal real roots, or complex roots. Okay, for the next slide, I will pass to the next presenter. Thank you.
So thank you, Amma. So for the next slide, I will explain about the example of a distinct real roots. So next, we will look at an example involving distinct real roots. Given the differential equation y double prime plus 7y prime plus 10y equals to 0. First, we must form the characteristic equation, which is r squared plus 7r plus 10 equals 0. By factorizing, we obtain two different roots, which are negative 5 and negative 2. Since the roots are distinct real roots, the general solution is C1e to the power of negative 5x plus C2e to the power of negative 2x. Therefore, the final answer is y equals C1e to the power of negative 5x plus C2e to the power of negative 2x. Now, let's consider an example with equal real roots. The given differential equation is y double prime plus 4y prime plus 4y equals 0. So first, we must form the characteristic equation r squared plus 4r plus 4 equals 0. Next, factorizing gives us the repeated root r equals negative 2. Because both roots are equal, the general solution contains an additional x term. Hence, the solution is y equals open bracket c 1 plus c2c close bracket multiplied by e to the power of negative 2x. Therefore, the final answer is y equals open bracket c 1 plus c2x close bracket e to the power of negative 2x. Next, we move on to the example involving complex roots. The differential equation is y double prime plus 4y prime plus 13y equals 0. The characteristic equation is r squared plus 4r plus 13 equals to 0. Using the quadratic formula, we obtain the roots negative 2 plus or minus 3i. Since the roots are complex, the solution involves exponential, sine and cosine functions. Therefore, the general solution becomes e to the power of negative 2x multiplied by the quantity c 1 cosine 3x plus c2 sine 3x. Hence, the final answer is equals e to the power of negative 2x times the quantity c 1 cosine 3x plus c2 sine 3x.
For the next slides, I will introducing about Laplace transform. Laplace transform converts differential equation into algebraic equation. For the definition of Laplace transform is L in bracket F in bracket T equals to lambda infinity 0 exponent power of negative st f t dt. For the advantages of Laplace transform is easier calculation, handles initial conditions directly, and useful in engineering system. Next, I will explain about the table, which is common Laplace transform table. This table presents several basic functions and their corresponding Laplace transform. The Laplace transform converts a function from the time domain t into the s domain, making the mathematical analysis and the solution of differential equation easier. The constant function 1 transforms to 1 over s. the linear function t transforms to 1 over s power of 2. The exponential function exponent power of at transforms to 1 over s minus a. The sine function, which is sine at, transforms to a over s power of 2 plus a over power of 2. The cosine function, which is cos at, transforms to s over s power of 2 plus a power of 2. These standard transform pairs are commonly used as reference when solving engineering and mathematical problems involving Laplace transform. Next, I will explain about the properties of Laplace transform. This slide highlights the main properties of the Laplace transform that make mathematical analysis easier. These properties help simplify complex differential equations into algebraic equations that are easier to solve. For the first one, which is linearity, it allows multiple functions to be transformed separately and then combined. For the differentiation, converts derivative in the time domain into algebraic expression in the S domain. For the integration, it simplifies the transformation of integral functions. For the time shifting, it describes how delays or shifts in the time affect the Laplace transform. These properties are widely used in engineering, mathematics, and control systems because they simplify the process of solving differential equations. For the next slide, it show about Laplace transform of derivative. This slide shows the Laplace transform formula for derivative. These formulas allow differential equations to be converted into algebraic equations in the S domain, making them easier to solve. For the first formula, which is L in bracket y prime equal to Sy in bracket S minus y in bracket 0, which is the Laplace transform of the first derivative includes the initial value of the function, which is y in bracket 0. For the second formula, which is L in bracket y double prime equal to s power of 2 y in bracket s minus sy in bracket 0 minus y prime in bracket 0, which is the Laplace transform of the second derivative includes both the initial value, which is y in bracket 0, and the initial derivative, which is y prime in bracket 0. These formulas are especially useful for solving first-order and second-order differential equations, which are commonly encountered in engineering and physics.
Now, let's take a look at an example using the Laplace transform method. We are given the differential equation y double prime plus 3y prime plus 2y equals 0 with the initial condition y0 equals 1 and y prime 0 equals 0. First, we take the Laplace transform of both sides of the equation. Then we substitute the initial condition into the Laplace formulas for the first and second derivative. This converts the differential equation into an algebraic equation in terms of ys. Next, we simplify the algebraic equation by collecting all terms containing ys. After rearranging, we obtain ys equals s plus 3 divided to s plus 1, s plus 2. At this stage, the differential equation has been transformed into a simpler algebraic expression, making it easier to solve. Finally, We use partial fraction decomposition to separate ys into simpler fraction. This gives us ys equals 2 divided by s plus 1 minus 1 divided s plus 2. By applying the inverse Laplace transform, we obtain the final solution, which is yt equals 2 exponent negative t minus exponent negative 2t. This example shows how Laplace transform can simplify the process of solving differential equation with initial condition. In conclusion, second-order differential equations are important in engineering because they help model and analyze real-world systems. We learn how to solve homogeneous and non-homogeneous equations using different methods, including the characteristic equation method and the method of undetermined coefficients. We also saw how the Laplace transform can simplify differential equations by covering them into algebraic equations. Overall, these techniques are valuable tools for solving engineering problems efficiently. Thank you.
That's all from us. Thank you.